we can start.
Yes, sir, we will start officially. So you're be ready with PPT, I guess, sir. So we'll have an official invitation and then we'll start. Okay, sir?
Sure.
Okay, sir. Okay, thank you.
Ma'am, we can start. I'm setting another device, so.
Okay, okay. Yes. Yeah, sure, sir. Janita? Janita? Yes, Janita, are you online? Hello, Janita? Janita, are you there? Ramya? Ramya or Janita, are you online?
சைடு போவீங்க
Janita, I think I can start now. Janita? Miss Janita? Janita, are you there? Okay, sir. A warm good evening to all the participants who have assembled here. And good evening to our guest, Dr. Siddharth Nair. Thank you, sir, for accepting our invitation and joining us for this FTP. And participants, you're also welcome to this session. As you know, we are having the third day session today. And a brief introduction about the 5 days hybrid faculty development program. Our institution is celebrating the 25 years. And as a part of it, we are organizing many events, technical events, both competitions also. And as a part of this 25-year celebrations, we are having a 5 days hybrid FTP on innovative healthcare, leveraging AI and ML for advanced biomedical signal analysis. We have a 5-day program. Out of this, we are having academicians, researchers, and also industry persons. And today is the third day of the event. And here, Dr. Siddharth Nair, who is the founder and CEO for a Bangalore-based company known as Zurion, is here. As you all know, sir is very busy with his commitments, and he has readily accepted our invitation to be part of this FDP. Thank you so much, sir, for accepting our invitation. and being part of this. I'm sure that our participants, the participants are actually faculty members, they are research scholars also, and some of the faculty members are doing the research also in this field. So definitely, I know that these people will be greatly benefited by your session. Thank you, sir. And Benita, Benita, Janita, can you read the profile now?
Ma'am, she's not available. I'll read.
Yeah. So I welcome Ramya, Miss Ramya of EC department to please introduce the guest of the day. Over to you, Ramya, please.
Thank you, ma'am. We are honored to have with us our distinguished resource person for today's session, Dr. Siddhartha Nair. Dr. Siddhartha Nair describes himself as the chaos alchemist, building cognitive system that transform movement into medicine and mischief into measurable growth. He is the founder and CEO of Zurion AI and the creator of Memo, a brain-body console that helps children and elders rewire focus, coordination, and joy. He is an experienced healthcare and technology entrepreneur working in the areas of neuromorphic computing, neurotechnology, product design, R&D, medical technology, and artificial intelligence. His mission is not to fix brains, but to unleash them through science, innovation, and purpose. With great respect, I now invite Dr. Siddhartha Nair to begin today's session and enlighten us with his knowledge and experience. Sir, the session is over to you.
Thank you. I hope my screen is visible to all.
Yes, sir. Yes, sir.
So I'm sorry, today's topic is quite big and broad, but so basically, as you all know, it's about how do we design intelligent medical devices with which has biosensors, and how can it be used for preventive as well as reactive healthcare, and how Zuron has built a platform and how it could also be useful for researchers and academicians like you all. That's the whole idea. So, of course, the MC here did read about what is there in my LinkedIn profile, but giving a brief background otherwise as well. Though I've been like I did my bachelor's in bioengineering and master's in medical electronics from CEG, PhDs from ISA Bangalore. But while doing this entire academia, during my bachelor's, I had worked on about roughly 20 to 24 projects. Uh, during my master's, I built my first startup, Fiesta, where we were building a neuromodulation device, non-invasive neuromodulation device, which was an advanced system, advanced tense basically, having a complete intelligence system. Anyway, sorry. All this thing happens in an online call. Sorry for that. So basically, which was an intelligent medical device itself, and that was commercialized. It was built for my mother. She was with diabetic neuropathy, and when she was using it, we worked on kind of how can we revive the neurons and get back her sensation, and we were successful. We sold some 75 plus units, and post that, of course, commercialization is always hard, and that's when I stopped the startup back then. And this was being done while I was pursuing my masters at CEG. In fact, base grant was given by CEG way back in 2012 itself. So that's how it worked. But post that, I while doing my masters, I saw that brain has a lot of potential. At the same time, even the most common disease called as diabetes also has connection with brains, right? So what happens in diabetes is we all know that sugar levels are high. True. But if we look into the root cause of why these sugar levels are high, people will tell it's about insulin resistivity or insulin sensitivity, etc., etc., etc. Right? And then if you control your food, you do exercise, it will it will be better. But all these are symptoms, right? It's just the symptoms. The idea is how do we look into the root cause of diabetes? So let's take that as an example and take it forward. So now for diabetes itself, you see, there is a part of your brain called as hypothalamus, and hypothalamus is is the most important part which looks into the overall sync between your pancreas and your brain. And pancreas, kind of regulates your insulin. So when you are constantly stressed, the control loop between hypothalamus and pancreas starts breaking. So thereby pancreas will keep secreting insulin, but the brain will not know how much insulin is available. For a typical human whose sync is perfect, what would happen is when pancreas is releasing insulin, the brain will know, okay, this much insulin is released. Accordingly, it will figure out how the metabolism would work, and basically your sugar levels get controlled. But in the other scenario, the blood sugar is continuously going high, and then there is also, because a lot of insulin has been secreted, there is an insulin resistance that comes in. So thereby the body is less sensitive to the insulin. So even if the insulin produced is more, the blood is not absorbing that insulin, and thereby the sugar levels are not coming down, right? So this is what happens. And now uh, and that's what leads to your entire sugar being high. And when sugar is high, it kind of affects all other cells, and then you have a systemic multi-organ damage that can happen with diabetes. As you know, there is diabetic retinopathy, diabetic nephropathy. So that's the huge chain that we have. And it all starts in your brain, hypothalamus. And the major cause is all our personal lives, thanks to the stress that we all have, right? So, so even a condition like diabetes had relationship with. Similarly, we also found in our research that the conditions these days, which are so spoken about, like PCOS, PCOD, thyroid fluctuations, etc., etc., etc. Most of this do originate with brain. And when it comes to brain health, the best part people talk about is nothing but mental health, right? So you do yoga, etc., and all those things. But for last so many years, we are used to screen so much that half of the generation has ADHD, and we cannot really silently sit and do yoga. So most of us fail doing it. So what's the alternative? That's what we were starting to look into, and we started to build. So while building, we did a lot of things, and I'm coming to that. And I'll just quickly give a small idea of what we have done in a minute. Post that, I would go and deep dive into something around intelligent medical systems, how it is designed. And then finally, I'll also come back to how Zurion is helping, people like you, doctors, etc., to kind of solve various problems and go to market faster. So all the researchers could actually also use our platform. That's how we are gonna, manage this entire session. So very quickly, so Zurion, we are building a brain and body training tool that helps children and seniors, that is, children with neurodevelopmental conditions like autism, ADHD, cerebral palsy, etc., and seniors with neurodegenerative conditions like Parkinson's, Alzheimer's, dementia, to either gain or regain their abilities through the medium of games. Why? Games is one place where we all are, like, in our young days or childhood, all of us used to play. But as soon as we turn 18 or we get into college, that's the first thing that goes out of our, at least for many of us. Some of us continue, and that's good for them. So this is where we started to look into it. And that's what led to our vision, where we are looking into a world where every mind can learn, relearn, recover, and perform better through intelligent play-based therapy. That's what, as a one-liner, that we have been building. But so I'll not get into the problem, solution, etc. here. There is a lot of it, but I don't want to get into it. Rather, what I want to do is I want to show what we have built and how it works. Once that is done, I would like to take you about something that is common across all the intelligent medical devices. So I hope you are able to see this demo now.
Yes, sir, we are able to see.
Yeah. So basically, this is what we have built, where we have our own console. We have multiple sensors, including computer vision, IMU. We are partnering with Anna University for EEG, etc. And people play games physically in the digital world. And when they play game, we look into their cognition, that is the processes that goes on in their mind, and we look into the biomechanics of a person. So that's what this entire platform has done. So we have been using it for people with stroke, cerebral palsy, autism, ADHD, Parkinson's, and multiple other conditions. And trust me, the connection between how your neurons work and your muscles work has a straightforward connection and reconnection with the brain. I can go all about brain in if required, but I think we need to go and look into the design aspect as well. So I'm like stopping this here. But this is what we have built. But while building so, just wanted to give you an idea that it doesn't stop here. We have built a complete ecosystem where developers can do a lot of things, etc., which I will come back to you in a minute. But before that, let's get into the intelligent. So I like to go traditional. That's why I thought, okay, let me use all of us, all of you are faculty, so it becomes easier to write rather than keep talking at a present. So if we see, most of us are almost all are engineers here. So if we look into our work, we all know what is a control system. It has an input, has a process, and it has an output in a very simple way, right? Now, if you look into a medical device, any medical device, at in today's world, what's happening? In today's world, what happens with medical devices? We all start having a sensor. You take any condition. You are talking about, say, a glucometer. You have basically your biochemical sensor strip is there. So you use a lancet, prick it, put the blood on that small sensor, and then there is a control based unit, and then it gives a readout. So that's how glucometer works, right? In case of blood. But now, if we take a scenario about other scenarios, like not just blood glucometer and all those things, but let's take a little more complicated device like EEG, right? So now, even in EEG, if we see, we have a same scenario. So we have the electrodes which are kept on the scale. Then there is an analog processing. If you look at the EEG machine, and then it goes to uh, the EEG machine, which has all your digital processing, etc. And then the final thing is the EEG thing. EEG is looked into the readout. Right? Now let's take a little more complicated case of EEG based solution. So if so I'm sure you all know this, but I'm just trying to make a point here. So you'll have an EEG electrode. With that, you will do a processing. Then you may take that processing to a PC to further do feature extraction. and then from PC you may again send it to either say a wheelchair to control easy controlled wheelchair, or you may take it to the say make some sort of EEG control games you can have it, right? Or you could do EEG based say cognitive diagnosis, right? So cognitive diagnosis. Sorry. So you will do cognitive diagnosis. So now the problem, where is the problem over here? We all know this. This is what happens. Same thing is scenario with EMG. Same thing is scenario with so many different conditions. So now where is the problem? We all are repeating and not doing the research which is required to further the thing. Most of us get stuck up in building the EEG amplifier, which is in the processing block, or we may end up making a PC based application, or we may end up either making a wheelchair, we may end up making games, whatever it is. So this is what is happening today. Now the same thing, if you take out EEG and put EMG, it's the same thing. Put ECG, it's the same thing. Put PPG, anything, any biosensor you want, it's a similar scenario. Same. So we are just repeating as a nation. Firstly, okay. Secondly, what we are doing, either we end up making it as a microcontroller based. Okay, that is pure microcontroller. There is no PC involvement. The entire process is happening in microcontroller, just like an EEG machine, and it has its own display, and you get it display. Either we start doing like that, or we end up making a complete PC application. That means microcontroller is used only for uh, basically the EEG amplifier analog signals, or AFE is giving a data. You use the microcontroller to send it across to the PC either using wire or wireless. So basically, microcontroller is just to kind of converse between the analog system and the computer. That it basically either just works as that, and then all your application goes into PC. Now, next what happens is you will end up building a complete PC application. So you'll have say a quad-core system or whatever it is. It's gonna do so many processes, right from digital signal processing to all filtering, all the digital filtering to your feature extraction to whatever final outcome that you're gonna have. So this is what typically is happening. But imagine, can we make this intelligent medical devices using what I call as basically one distributed processing, which you can also name as edge. But typically, when the word edge compute is used, it's basically currently means that you're using multiple smaller PCs to do a process, and then it goes to the cloud, and then there's a most thing. That's how typically the edge means. But can we do a distributed processing, which could which has an intelligent algorithm, which could manage your PC processes, your controller processes, and your analog amplification very well. We cannot do much in analog amplification because those are your chips, so we can't do much. But can we do a lot around the other design of it? So that's where what Zurion started to do was, we did recognize this problem because, as I told you, I've worked on a lot of projects over last. I finished my BE in 2011, and since BE, and I'm Is my voice clear to everyone, or there is some problem?
Yes, sir. It is clear, sir. Please proceed,
It's clear.
sir.
Yeah, sure. So, so basically, as I've been working with so many processes, so many things, we recognize that we all are doing the same thing. I'm sure I know personally a lot of researchers doing same thing again and again and again, and not end up, kind of working on the research component, but working on these components all the time, and then hardly we have some time to do research components. Same thing is happening with student projects. All the student projects start with all the same things, and then it never goes to the market because this is how we've been doing it forever, and there is no standardization aspect. That's where what we realized is this is not just a hardware problem. This problem has to be solved in multiple. For example, for microcontroller, right now we write a program. Most of you guys would use say Arduino or ESP or something. You have to write a program here in microcontroller. So majorly it would be a hard code program that you write. And as I had told earlier, you may just probably use it as a DAC and don't do much processing over here. But today's microcontroller has the ability to have as most of the time, like say you have controllers like ESP32S3, which has AI cores within small AI cores for action detection, feature extraction. There is some aspect of it, right? At the same time, we all know RTOS, but none of us technically uh, technically write a code on RTOS, right? None of us use it. We just use it as a program, as I told earlier. So there is RTOS, but we don't use it. And if you see RTOS, only only RTOS that most of us end up using, if you use this also, either free RTOS or ESP IDF or some basic art. Even ESP IDF ends up using. There are not much RTOS. So RTOS becomes the first. Now, secondly, if you do see, so this is the problem in the microcontroller area. Okay, problem one. Then there is a problem two. Problem two is basically in your PC. Most of us, what we do, we end up writing uh, basic code on MATLAB or LabVIEW, which are both for Windows. And now, when it comes to medical device, the process is critical, right? But I would like to just share my screen once more, my laptop screen once more. Right now, it's my tab screen that's being shared. Uh, okay, and I want to kind of take you to my task manager. Okay, so currently, I'm using a Windows laptop, and I guess I hope you can see the screen. If you see my processes,
Sir,
of course,
excuse me, sir. Your
yeah, ma'am.
screen is not visible to
Is
us
this the
now.
yes? Uh, is it now visible?
Yes, sir. Yes, sir.
Yeah. So this is how the current processes are looking like in my laptop. Without doing much, I'm just right now using my Teams, and it is like kind of continuously using 11 to 30-40% of my CPU. I am right now using 47% of my memory, and I want to show you that I have 32 GB of RAM. In that 32 GB, I am almost consuming somewhere around 16 GB of my RAM. Straight. I have a 4 GB GPU, and I am also consuming my GPU at this point of time. And if you see my processor, I have a i7 10 Gen processor, which can go up to 4.06 gigahertz. So if you can see the speed over here, it is right now running anywhere between 3.9 to 4.6 gigahertz. Now, when you have a critical application running on your Windows system, right? With regards to something in medicine, and when your processors are not, and same thing, I'm sure if you guys open your task manager, you can see the numbers being very different. Most of us may not have a laptop with 32 GB RAM. Few people would have, but not most of us. Most of us may have 8 to 16 GB RAM. Very few of us will have 32 GB RAM. Some of you will have 2 GB graphics to 0 GB graphics. Some of us have 4 GB. When your hardware specification is so different, your windows using the processors are so different. To run one more application, will two application give the same outcome? To be frank, answer is no, it cannot. Because the way your system is processing that application, okay, it's gonna be different for different laptops due to the load of applications. So that means I'll again share my whiteboard. Yeah. So if you can see my screen. So in PC, when you have, you know, no standard PC with everyone, and the OS doesn't have control on its thread, control on processes. In our application, if you build, we don't control the processes in the system, right? And at the same time, varied loads. So basically, it will all depend on how good you have written your PC. Most of us may have written very badly, and that's the reality, unfortunate reality. So now in this scenario, when you don't have a standard PC, how do you think your whatever research we do, whatever application we have built is really up to the mark, which could solve the problem, give you the right answer, and at the same time get it right? Answer is no, most probably not. Right? So this is the second problem of PC application. Third problem is sensors. Now, most of us end up using Amazon. You get some sensors. You may be just buying it, or something, from somewhere else, which may not be a standard sensor, but just for, let's say, for a jugaad purpose, you would have bought one sensor and use it, or an amplifier which we have designed as a custom board, or which may or may not work perfectly, right? So at the end of the day, you have a non-standard sensor most of the time, and only when you are really working on a sensor you may standardize it. But in typical world, in a research aspect of it, in your academic aspect of it, we may not be using a standardized sensor. That's the third problem. So when all the three variables of a system has an issue, do we think we are making the right kind of a device? Leave of AI at this point, right? In all these things, AI coming up, sometimes few of us may make some ML application or pattern recognition applications in the PC, or some of us may make some kind of action detection in the controller, but hardly any intelligence that goes into it, right? Most of us end up generating a lot of data, sending it to cloud, and then building a cloud application to kind of do AI, right? But do you know, I pay almost 40 lakh rupees per month, sorry, 36 lakh rupees per month on my cloud infrastructure at Zurion to GCP and AWS together. For Because overall infrastructure is expensive. So if we are talking about AI in health or intelligent medical device, it doesn't work really good. Now, if my load, and this is after I shared my load locally, but if imagine I don't share, it will not. At an industry level, I'm spending this, but can we all do that? I have no answers. So now to do all, now imagine a technique before we get into the Zurion bit of it. Let me kind of propose a small framework which probably would make sense to most of you. In fact, almost 7, 8 years back, I did propose a similar framework an IEEE paper to a conference, but there's an add-on because that time AI was not that there, but I did give an intelligent embedded system over there, but not with the PC application. So this is an upgraded framework on top of it. If you look into my name and Google Scholar, you may get. So it was part of a IEEE conference in SSN Chennai, uh, probably around 2018, if I'm right. Anyways, so now coming back to an schema for intelligent device, which will start making sense. Let's say, let's say you have your, I'm calling it as intelligent sensor or input. So in this case, let's say you have your sensor, your analog processing, your DAC conversion for the microcontroller, and then it has two layers. One is raw data storage, either on a SSD, micro SD, or flash memory, and a feature extractor. So this is why I'm calling this intelligent. I'll give you an example in 1 minute. So, and I'll tell that what we have done itself so that it makes more sense. Okay, let's start telling and then I'll keep adding on to it. So what we have done is, I'll give you one small application that we have built, and it's called as balance board. So in the earlier demo, if you have seen, mm, in the earlier demo, if you have seen, I had shown a person kind of going in a balance board, and giving the example of the same balance board. So what we and at Zurion did for this intelligent input is you can have multiple IMU sensors, just IMU, nothing else, right? So what we did is in the balance board itself, we basically did the uh, IMU. IMU is fortunately IMU is a digital sensor, so it gave me a digital record. So I did not require an analog processing in this scenario. Okay, but IMU itself was going into an ESP32 slave board. So in this, we already have had an AI core. So in this AI core, what I did is I wrote a three-level application. So based on how it works, I'll give you in a second. I wrote a three-level application here. So in level one, it would look into balancing. So balancing is nothing but if a person stands on a balance board, are they going to left, right, forward, backward, or if they're standing, are they standing straight, something like that, right? So one is balancing. Second, I connected it to gate, the way we all walk, right? So, and third, great. So second option was gate analysis. And the third layer that we in that did was we kind of added it into a dynamic balancer. So dynamic balancer as an upgrade. I'll get back into dynamic balancer later. So these were the three applications in the AI core. So same sensor within the system could be used for three different applications, and the sensor used to get configured based on the input signal in real time, right? So now, next that we did is we did the wireless connectivity. So basically, connectivity plus storage. So basically, whenever the application is, one, it kept on storing, and second, it kept on doing the feature extraction. And now it used to do is real time. It just sends the feature extracted, and in the later time before it ends, it will send out all the raw data. What we do with the raw data and the feature set, I will tell you right now. So we had two outputs out of this. One is raw data, and second is feature extraction, features that were extracted. Now at the level two, what we had done is we have a PC that is basically called as Mimo. I'll show the photo of Mimo in. In this, we connect one hub. So this is the mother hub which can control up to 12 sensors. At the moment, we'll be getting to 20, 30 sensor hubs in near future. Currently, up to 12 sensors. So what this hub would do is it would do two-way communication. The PC, based on what is the user using, the PC will tell what happens. Hub will control the sensor required, and the hub will tell what application to select. Say it sends one, balancing. If it sends two, gate. It sends three, dynamic balance. And in this, you already have an Zurion ATOS, which is currently a feature on FreeRTOS, but we are working on kernel as well, so that we can do on the air updates as well. Will select the application. Based on this, your intelligence input basically gets configured. When you're doing it, the feature is sent to the Mimo in real time. Based on this, whatever application has been written, so when this application run, it sees to it that all other, except for the bare minimum processes that are required, all other processes get killed, and only this main application process starts running. Now, in this application, what happens is it does the balancing or gate or dynamic balance as required. It will run that application. Keep working. The user will play. While user playing this, we would again do a feature extraction. In this case, the post through camera, through camera. Uh, your basically which gives us the cognition, biomechanics, and it would also run and also the uh, uh, input uh, feature, that is in this case direction. If it is balance, in case of gate, it will tell the joint angles as required. So input feature it will. So this is all happening in real time. Now, at the end, and the user plays the game, you get the result, etc., etc., etc. All those reporting, whatever is required, it happens. But in all this thing picture, there is an OS which is controlling all of it, which we call it as Zurion OS at this point of time. And right now, it is a distribution out of Fedora. But we will be soon. We are also adding a feature set which would kind of where we are modifying the kernels for our applications, and for the neurocomputing that we are calling as. I'll come to neurocompute in the next 2 or 3 minutes. So now with this application, this thing overs. As soon as the application gets over, all the raw data comes back. All this post data, etc., also goes back to federated learning system. Federated learning system. Now, this federated learning does your entire DL version as well as ML as required, so that your overall AI application keeps learning and making more sense of data what it gets, and then only the learned model is sent back to the cloud. So everything happened locally, and the final thing goes to the cloud. On the cloud, the main model is continuously improved, basically uh, which is basically your foundational model of brain that we have been building, right? Now, this foundational model of brain has led us to build something called as neurocomputing. So as I told you, we'll talk about neurocompute for a couple of minutes. So neurocomputing is very similar to how a brain works. If you all know, brain has four parts. That four you have eight again subparts, and then each of it controls your speech, controls different senses. You have your spinal cord, which controls your reflex actions. Some parts do cognition, some part manages muscles. All of this, right? Same approach we are now bringing into a compute as well. Rather than having just one core, when I say one core, that is one processor which has four physical core and 6 to 8 logical core based on your system config. We are building a system where we have multiple processors at a smaller levels, which could, like your brain, run different segments of. That's what is neurocompute in the hardware layer that we are working. But before we get into hardware, what we did is we used the existing x86 or ARM architecture. Currently, we are working on x86. We are soon migrating to ARM architecture as well. On that, we are adding Zurion OS. So Zurion OS now works similar to this. So we at the moment, instead of playing too much with hardware because hardware becomes expensive to build, we kind of played on the operating system and used the same principles of your brain in the operating system, embedding the AI right inside your OS, and thereby making the processes much better, much faster. And we are able to run deep learning applications in i5 fifth generation models. So you can i5 today is i5 13 generation that's going on, but we are talking about fifth generation in which it can run really fast. So that's the kind of thing that we have already built and we are improving on top of it with Zurion OS. So if you see here, the AI part in this entire thing, we have distributed.
Okay, fine. Is it okay, Ramya?
Alright.